My name is Matt Ledger. I am the North American North Central Regional Sales Manager for API, and I'm here to show you the API arm. The arm that we have here is our 2.5 meter arm. This model does come in a 2 meter, 2.5 meter, 3 meter, 3.5 meter, 4 meter, and 4.5 meter. And that basically describes the spherical diameter that it can work in. This type of arm also comes in two different models, where one is a 6-axis and one is a 7-axis. That basically refers to the amount of axis that it can move about. So we have 1, 2, 3, 4, 5, 6, and this model has an additional 7th axis for scanners. The scanner that is on this is the ACE Skyline scanner. It measures 600,000 points a second. And the accuracy is right around 48 microns. This also can be removed to include a probe on the end, where your accuracies will become better than the scanner. So initially, when it's just a probing arm, the accuracy single point repeatability is 27 microns, or just over plus or minus 1/1000th of an inch. When you add the scanner onto it, you're getting about 48 microns, or just under plus or minus 2/1000ths of an inch. So definitely very accurate. This arm, as you can see, is made of composite tubes that helps with any kind of thermal expansion between the encoders. As the arm does get longer, the accuracy does decrease, or you add an additional 10 to 15 microns with each size that goes up. This arm has pretty nice features as far as the portability of it. This has a battery pack on the back that can give you several hours of working with no power plugged into it. This also has Wi-Fi capability, so you don't need to be connected whatsoever to the computer to take this into a shop and measure. When the scanner is attached to the arm, we do need to be plugged in through Ethernet, because the amount of data flow that comes out of the arm, we need that wired connection. A couple other nice features of the arm is that the handle grip is very ergonomical with 3 different buttons on it. One button is a trigger pull, the next one is a trigger push, and then there's a button on the back of the arm. Each of those buttons can be programmable to either take a measurement, delete a measurement, or finish a measurement process. Another nice feature of the arm handle is a magnetic docking that it has. It's a really nice fitting that it has, and it's a very strong magnet, where you don't have to worry about the arm falling off or getting hit off. It's got really solid connection to it. Also, what comes with the arm is a toolkit, where it has every component needed to swap in between the scanner and the probing unit. Also calibration spheres for both probe and the scanner. A base comes with it for tabletop mounting. This is a 3.5-inch thread, which is also what this has. This is a standard 3.5-inch metrology thread. So a lot of your stands that you already have or being used in the market will fit with the arm. There's also a dust cover and a portable carrying case. Very protective carrying case too, that can ship easily and don't have to worry about damage. Inside the kit, I am going to pull out the probe that comes with it. This is a standard kit where it includes a 6mm ruby tip. The nice part about these ruby tips is that it's modular for the whole base attachment. There's 3 components to it: the actual tip, a spacer, and the base. This base has data information inside of it that will carry your calibration of that probe no matter what computer you go to. It's all stored in the probe. The nice part about it being modular too is that if you want to swap out the probe tip with a longer one or a different material, it's as easy as just buying the tip portion of it instead of purchasing a whole new probe assembly. With these probes, we're not defined to one manufacturer. This is a Renishaw base, but all these probe tips have the full breadth of the Renishaw catalog, as well as any third-party manufacturers as well. So again, this is really nice, where if you break it or need to replace it, you're not paying for hundreds of dollars for the whole probe assembly. You just swap out the probe tip. So now I'm going to demonstrate installing the probe onto the arm and then going through a calibration process. So there is a key inside the toolkit, and what we're going to do is we're going to index the probe tip onto the arm, and then we're going to use the key to lock it on. Next, I'm going to grab my computer, and we're going to go through how to connect to the arm, check diagnostics, see if the arm is ready to be run, and then we're going to go through the probe management, and we're going to calibrate that probe. Okay, so we're going to plug in the arm into the computer. We're going to do this via USB. When you install the drivers for this arm, there is a arm wizard that we'll go into to connect. So we're going to double click on it, and we're going to hit connect. Then it's going to ask us what profile to select. So we're going to just deal with the probing aspect. So I'm going to say probe. Now it's asking us to unstow the arm to exercise each encoder. So as we move it, we can tell it's checking it off, and then finally the additional scanner axis. So now the arm wizard is reading out. We see numbers running. We're basically connected to it. From here, we can go into the calibration probes management. So this screen is basically where we can add new probes or modify the existing probe. What we're going to do is we're going to modify it by adding a calibration. So in the kit that I was telling you about comes the drivers, comes all the tools to be able to install it to a base, installs the key system for the probe, and it also includes 2 spheres since we're using the scanner with it. This sphere is the one that we're going to use for the calibration of the probe. So the process would be to fixture it down to your table. This can be done with a clamp or hot glue. Just any way where it won't move. And then right here in the probe management, it asks us to put the qualifying sphere diameter. And it says it right on the side of here. So we already have it in there. It's 20.0019 millimeters. And then it's asking us to take at least 15 points. So I'm going to unstow the arm. And I like to do 4 around the widest part of the sphere, 4 around the upper part of the hemisphere, and then 1 right on top. I'm going to position the arm differently and do that again. And then maybe 1 in this orientation. When we're done, we stow the arm and we hit compute. This screen will give us a upper and lower point graph. It'll also tell us the sphere diameter that it had calculated. And it'll give us a sigma rating or the deviation from the nominal sphere diameter. So we're at 26 microns. That's within the 27 micron calibration standard. So we're going to hit save and apply. Now that I described how to calibrate the probe inside of the arm wizard, I'm going to demonstrate how to install the scanner and do a calibration on that. When you go from switching between the scanner and the probe, you should shut off the arm. Then we're going to take our key. We're going to remove the probe. We're going to grab our scanner, put it in unlocked mode, place it on, lock it on, and turn the arm back on. So again, the arm is connected through the Ethernet port. During the installation process, the drivers will configure your Ethernet adapter to connect automatically. So I'm actually going to go through the calibration process in the third-party software, and then I will install the probe on it, and we'll go through a calibration with that. So for this sake, I'm going to be using Verisurf. Also, while that's firing up, I'm going to take my tool, and I'm going to remove the sphere that we use to calibrate the probe, and we're going to install the matte looking sphere. So the scanner needs a different type of sphere because of the reflectivity of the other sphere messes with the calibration results. So this sphere was specifically manufactured for the calibration of this scanner. When we open the device manager in Verisurf, we're going to be on the laser scanner device. We're going to hit start. It's going to ask us to select the profile. We're going to select scanner. Again, we're going to unstow it and exercise each axis, including the scanner axis. And now we are connected. So now that the arm is started, in our device controls, we're going to hit the calibration button. I have a previous scan in there, so I'm going to delete it out. And then it asks us here to put in the nominal diameter of the sphere, which is written on the side. That's 34.999 millimeters. When we're ready to record, we're going to hit the record button. And then we're going to trigger to gather data. So on the screen, the active scan will be colored red, and the gray portion is a previous scan. So it doesn't matter if you take some bad data like on the table or the clamp in this case, it's going to do a filtering later and pull out the sphere. So we're going to put the arm in different orientations. We're going to try to cover as much as we can. When we're done, we'll stow the arm, we'll press stop, and we'll hit compute. So right now it's filtering out a lot of the flyer data, table, clamp, and it's trying to pull out that sphere, and it's going to calculate it and give us our results of the calibration. So after it computes the sphere, you can see that it pulled out quite a bit of the sphere. We can zoom in, we can see what kind of data it collected. Below, we are getting the diameter of 34.997. So it's 2 microns below what the nominal diameter is. Really good. So from here, we're going to hit save. Now it's saving all that spec information inside the arm. We're going to hit close, and we're ready to go with the scanner. So now I'm going to demonstrate installing the probe onto the scanner, and then we're going to calibrate that as well. So I'll take the probe that I had before. I'll take my removal tool. I'll unscrew it. Then I'm just going to take the scanner off so you can see it better. So on the bottom, we're going to screw the probe into there. Use the tool to just tighten it down. So now that we have the probe installed, and this is kind of a shorter probe, but you can put longer ones on it. The longer probe that you install on it, you'll notice you'll probably get less of a tighter calibration on it. We're going to switch over to probe. Then I'm going to hit calibration. So I can actually put in by sphere. So I'll put in this sphere, 34.999, and I'll hit start. I'm going to unstow it, and I'm going to take points similar to how I took them with the probe and the chrome sphere. So 4 points around the big part of the sphere, 4 around the upper hemisphere, 1 on top, change the orientation. And when you're done, gonna hit stop. And it's gonna give us our diameter. We have 35.013, so roughly 14 microns above the diameter, the nominal diameter of the calibration sphere, so it was good. So I'm gonna hit save, close. So now we have a calibrated scanner, we have a calibrated probe. Next, we're gonna throw a part on the table, and we'll use the scanner and the probe to demonstrate how to use the arm for alignment, scanning profile surfaces, grabbing some prismatic features like a circle or some planes. So now that we have the part on a work table, we want to make sure that the part isn't moving. We want to make sure the arm is stable. If the part is moving or it has the potential of moving from touching it, we can either fixture it down with tie downs. A lot of times I would just use hot glue. So I'm going to hot glue a couple of points right around the part just to make sure it doesn't move. So now that everything's fixtured, everything's tied down, we have the model loaded. We are going to hit create target, and we're going to select our alignment holes, which will be these 4 on top. So now that we have those 4 holes selected, I want to tell the software how I'm going to measure it. So I'm going to highlight the targets, right click, say edit target. I'm going to make them a target type axis, and the measurement method is a plane and a circle. So what I want to do is measure a plane on the spot face and the hole, plane, hole, to get the exact location that I'd selected. So when I'm ready, I'm going to hit run auto alignment. Now unstow the arm. I'm going to put it into a good position of measurement. With these arms, you can get higher accuracy if you minimize the movement of the encoders. So this position is a really good working one, especially if that's the only position I need to be in during the entire inspection. I'd minimize the encoder movement to the 5th, 6th, 7th axis, where these ones are moving very minimally. So now it's asking me to measure 4 points for the plane. Now 4 points for a circle. Now move to the next hole. I'm going to get that far hole. So now we have our results, and we see that our RMS is 1,001/10, so it's a good alignment. All the holes are in position, pretty much under 1,000ths in any direction. So I'm going to accept the alignment. Now, VeriSurf, after your alignment by default, is set up to immediately put you into inspect mode. Basically what that is a real-time comparison, and I have surfaces selected, so it'll be a real-time part inspection of the actual condition against the model or the nominal. So on the screen it's telling me -3,000ths, which basically means that the actual part to the hole alignment is 3,000ths lower than perfect. Our tolerance is set up right now as a profile of 4,000ths, so ±2. Anything above or below ±2 will be red or orange in the negative, and anything above it will be blue. So what I can do during this mode is actually trigger. and start collecting data. So I can either just touch trigger, I can press P on the keyboard, which switch it into continuous point mode. I can gather a lot of data, or I can switch it over to the scanner. I'll put it into automatic exposure mode. This will basically set the exposure to either a shiny surface or a dark flat surface. So the nice part about a blue light laser is that it has a high dynamic range, so it can switch in between those darks and flats to shiny or glossy silvers or brighter colored stuff. So it minimizes the amount of spraying you would have to do on some parts like you had to in the past. So now I'm going to highlight those same surfaces, and I'm going to hit inspector build mode again. Now I'll go ahead and start scanning measurements. So now we can see we have quite a bit of data on that surface. Just in a few seconds, that took over 40,000 points. So I just selected 2 small surfaces on the part, but this scanner does spit out 600,000 points per second. So now I'm gonna measure the sides of the part. So I'm gonna hit measure a plane. We'll do 4-point planes on them. So that information at the bottom of the screen will tell you the flatness. That plane was flat within 7/10,000ths. That one was flat within 9/10,000ths. That one's pretty flat too. So the nice part about the arm is being able to reach around parts, whereas some of the other devices, you're limited by line of sight. So this arm can reach around and under quite a bit. So now that we have some profile data, it's what the customer wanted to see. We have our holes and we have planes. We're gonna highlight everything we want to put into a report. I'm gonna hit report. And now here, I'm only gonna show what I'm reporting. We have our tolerance, our measured nominal tolerance, our deviation. So that's how I want all the holes to report. Then our planes, what we'll do is plane 1 and 2, they wanted no perpendicularity. Same with plane 4 and 3. And they wanted to know a distance between 1 and 3 and 2 and 4. So we see we're out of tolerance by just under 1/1000th of an inch on that distance, and we're within tolerance there. So what I'm gonna do is say I wanna only report the summary of all those points we scanned with. I wanna add a nice screenshot of it. I want to put that right above that inspection. Maybe I want to take a screenshot of the actual hole locations. Minus the balloons. So now we'll update our screenshot with the holes. Put that at the top. So from here, we can modify our header information, have some output settings that we can switch from inches to millimeters, decimal places. We can report out in PDF, HTML, or various types. But we're just gonna put out a PDF report. So basically we have our picture and all the necessary information for the report, including the profile screenshot. We have our perpendicularities and our distances between them. So that's it, PDF report. So that was a basic overview of the arm setup, the accessories that come with the arm. We went through the calibration process of probing and the scanner. We also have a part here that we use for alignment, scanning profiles, grabbing some prismatic data, and a simple report. And this part was just an in-process inspection part, but we could very well use the arm for final inspection. We can also use it to scan a part and reverse engineer it to a surface that we can use to machine or fabricate around. And also the arm can go straight to the machine where we can use a fixture plate to tie it down and check a part before it even comes off the machine. I think the biggest advantage of these things is that we can take the inspection to the part instead of having the part sit in a CMM lab with sometimes a whole turnover of a day. So this, with its dynamic thermal expansion settings inside the software and its thermal stability of the composite body, is able to quickly measure parts whether they're cold or hot. So if you have any other questions about the arm, or you want to schedule an in-person or web demo, please contact us at the information below. Thank you.